Hi guys, and welcome to this video on volume of a prism. Really good to see you. My name's Darren, MaffsGuru, which sounds a bit weird every time I say it out loud, and it is good to have you along. I'm going to explain in this video how to find the volume of a prism, which is good because that's the title of the video. And anyway, hold on, don't fast forward, it gets better, I promise. Now, if you haven't already done so, can you click on my subscribe button for YouTube? Again, it just shows me that you are watching, yeah? I don't know how many people watch these videos. I'm assuming it's just my mum and dad lots of time each night to make me feel loved. So if you click that button and subscribe, I'm just going to know that people are watching this, and it makes it all worthwhile. And then there's MaffsGuru, which is my website, free to sign up, with loads of videos in there, all organized by textbook and chapters with downloadable notes, and everything that you see them about to write on can be downloaded as well. So thank you for heading over there and signing up as well, and spreading the word. Tell your mates, TikTok, Instagram, and whatever else you guys are using now. All right, what are we going to do today? Well, knowing how to convert between units of volume is really, really important. Understand the difference between volume and capacity. Is there a difference? Coming up. Understand that prisms have a uniform cross-section. Have you noticed how maths is so annoying? Because it's got so many stupid words in it, like cross-section. The only thing I'm cross about is the stupid language we use, but anyway, right? But we use it for defining the volume and know how to find the volume of various prisms. What is a prism? I'll come back to that as well later. Now, obviously, we are building on a series of videos that are live on MaffsGuru.com that sort of teach you lots of different things. And we know that for things like prisms and volumes and surface areas and what have you, that there are certain base building blocks. There are shapes that we like to use that help us find three-dimensional shapes. So, for example, and the one I used in the last video, and we'll use it again, is a Toblerone. Oh, I love Toblerone. Yeah, now what's the whole point about Toblerone? If we look at that shape, it's basically a triangle at the front, a triangle at the back, and three rectangles. Don't believe me? Next time you're in Coles or Woolies or Tesco's or wherever you're watching this video, pick up a Toblerone and have a look at the front, the back, and the sides. It's just made up of basic shapes. So if we can find the area of a triangle, the area of a rectangle, the area of a circle, and obviously sometimes we throw in complicated ones like kites and trapeziums and rhombuses and, you know, parallelograms or whatever else. Doesn't matter. Those formulas or those pictures you've got there, if you've got them in your summary book or you just know these, you're going to smash this stuff, I promise. Now, obviously, converting units of volume, a recap of area. In previous lesson, I looked at how we convert between units of area. If you haven't watched the video, go and have a look. Using two-dimensional shape, we discovered that if we actually enlarged by a certain scale factor, the volume was the area was the square of the scale factor. My God, do I know what I'm talking about? So for example, if I had a square that was 2 by 2, we would know that the area of that would be 4 square units, yeah? If I now made that 4 by 4, because I've multiplied that by 2, because I've made it 2 times bigger, I know that my area is actually going to become the scale factor, which is times 2, but squared bigger. So let's just check. That would be 4 times, or 2 squared is the same as 2 times 2, which is 4, which gives me 16 square units. And does that work out? Well, that would give me an area of 4 by 4, which is 16 square units. All right, makes sense? If this had been times by 3, then this would have been 9 times bigger, because 3 times 3 is 9. Now, this was in a previous video, and we're going to use the same idea now for volume. So sorry, I'm going to rub all this out. So let's look at the same idea with volume. If we have a little square of 1 unit by 1 unit by 1 unit. Now remember, when we do volume, we do this times that, all right? So you choose one corner and you multiply them together. So in this situation, that would be 1 times 1 times 1, which would be in this situation 1 unit with a floaty 3. Why is it a floaty 3? Because absolutely it is volume. Yes, that's what I was thinking of and had a bit of a mind blank. So what I'm now going to do is I'm going to draw something, and I'm going to say it's now 3 by 3 by 3. So if I look at my volume here, if I look at that, what do I notice? It is, absolutely, it is 3 times bigger. All right, so I've taken that 1 by 1 by 1 and I've made it 3 times, and 3 times bigger. If we now look at the volume of this, that would be 3 times 3 times 3, which is 9 times 3, which is 27 cubic units. Oh, now what have we done, or what calculation we do to go from 1 to 27? Well, in this situation, we would times by 27, which just so also happens to be the scale factor cubed. Oh my goodness. So for example, if I had a shape that was 2 by 2 by 2, and I wanted to know the area of something that had been enlarged by scale factor, let's say scale factor 2, I find the volume of this, which gives me 2 times 2 times 2, which is 8, and then I multiply it by the scale factor of enlargement 2, but cubed. So 2 times 2 times 2 is actually 8, which would give me 64 units cubed, and ka-ching. So there is a way to be able to do this. What's that got to do with the price of fish? Well, basically, we don't like dealing with numbers that aren't particularly sensible. So what I'm going to look at now is the idea of making things 10 times bigger. Okay, so how is that important to me? Well, in this situation, let's look at the idea of going from centimeters to, centimeters to millimeters. Let's do that. All right, so centimeters to millimeters. We know we got 1 centimeter by 1 centimeter by 1 centimeter, which gives me 1 centimeter cubed. Now, how do I now get that into millimeters? Well, we realize that there are 10 millimeters in a centimeter. So each of now are going to be 10 by 10 by 10, which means that if I am going to millimeters, yes? So if I am going to millimeters, I will multiply that by 10 to the floaty 3, which will give me 1, 2, 3 millimeters cubed. Now the important thing there is this multiplier here. So what I'm trying to say is to go from any centimeters cubed into millimeters cubed, all I need to do is multiply by 10 to the floaty 3. That's 10 times 10 times 10. Now when we go backwards through it, what does that suggest? We would divide by 10 to the floaty 3. Because what we do forwards, we need to do backwards. And this diagram here is giving you the conversions from kilometers cubed into meters cubed, into centimeters cubed, into millimeters cubed, right? So for example, if I'm going from kilometers into meters, I'm going to times by 1,000 cubed. So I'm going to times by 1,000, times by 1,000, and times by 1,000 again. Why? Because again, 1 kilometer is 1,000 meters. So I'm getting 1,000 times bigger that way, 1,000 times bigger that way, and 1,000 times bigger that way. So that's why I'm multiplying by 1,000, 1,000, and 1,000. All right, so here are some examples. Let's look at this here. I've got 2.5 meters cubed into centimeters cubed. Right, so meters cubed into centimeters cubed, what does it tell me to do? Well, again, there's 100 centimeters in a meter, so I'm going to times by 100 that way, 100 that way, and 100 that way. Okay, so I'm just going to do 2.5 times 100 with the floaty 3, which is the same as 2.5 times 100 times 100 times 100. Now we know for every one of those zeros, I'm going to move my decimal point one place to absolutely the right. So that's going to become 2.5. It's going to jump 6 places. So 1, 2, 3, 4, 5, 6. Fill in zeros over all those jumps, and then write it out again to give me 2, 5, 0, 0, 0, 0, 0. And that is centimeters cubed. Gosh, that's huge. Yes, 458 millimeters cubed, so 458 millimeters cubed into centimeters cubed. All right, so again, now we're going backwards through it. So millimeters cubed into centimeters cubed. I'm now going to divide by 10 times 10 times 10, because I make it 10 times smaller and smaller and smaller. So 458 divided by 10 to the floaty 3. Now 10 to the floaty 3 is the same as, divided by 1,000, yeah? So 1 and 3 zeros. And again, we know when we divide, what do we do to my decimal point? I move it, yeah, absolutely. So at the moment, this would be 458 with the decimal point at the end. I'm going to move it 1, 2, 3 places, which is going to give me 0.458. So therefore, it gives me 0.458 centimeters cubed. So that diagram is really important. If you can, download the notes, stick it in your summary book, ka-ching. What on earth is capacity? Capacity is volume, believe it or not. but for liquids. All right, so when we are dealing with liquids, we actually deal with capacity. Same idea, to be brutally honest. You still work out the volume of these things in the same way, but you go, oh, it's a liquid. We've got to talk about it in liters. And again, we have some conversions for you here. I'm not going to explain them to you because it's very much the same as we had before. These are the ones, just cut them out, stick them in your summary book. But we have conversions between megaliters, liters, kiloliters, and milliliters. And if you do science, you will have met milliliters probably with pipettes or when you're doing some sort of chemistry type stuff. Yes, and again, some of the really important ones here are this. 1 centimeter cubed is equal to 1 milliliter. Really, really important. And one that we use ever such a lot, that 1 liter is equal to 1,000 centimeters cubed. That is so, so important because often we'll get you to work out the volume of something in centimeters cubed and then say what's its volume in liters or what's its capacity. All right, and that just means you can say, I divide by 1,000. A lot of talking. Now, find the volume using something else. We've always said the volume of a shape is equal to length times width times height. Well, actually, there's another way. And it is so much easier if you can think of it this way. What we look at here is if you look at this one times by this one, you're actually getting the area of the front of the shape. And of course, Barry is flippin' annoying and he's decided to give that a name called cross section. All right, so the front of that is the cross section, yes? Now, in which case we would then take that area of cross section and we would multiply it by how far back it goes. Because we've used this one and this one, it leaves just that measurement. So again, if you think about area, he says area, volume is equal to length times width times height. We know the width times the height now is called the cross-sectional area. And so we can now say that volume is area of cross-section times by the length. And again, length is fairly subjective. It basically means how far back it's going. Why? How is this important to me? Well, here we go. So find the volume of these three-dimensional objects. In this situation, I'm going to do it the old-fashioned way, and then I'm going to show you the other way as well. So in this situation here, we know the volume is equal to length times width times height. Right, well, let's call the length 1, the width 1, and the height is 3, which gives me 3 centimeters and cubed. Ka-ching. But actually, I'm going to say, well, what's the area of this front face here? Well, if we look at it and draw that square, we know it's 1 by 1. So the area of cross-section is equal to 1 times 1, which is 1. And I'm going to multiply it by how high it is or how deep it is. And so in this situation, my volume, which is area of cross-section times height, gives me, we know that that's 1, which we should really write as centimeters squared, by the way, multiplied by my height, which is 3, which once again gives me 3 centimeters cubed. Now you're sitting there going, why on earth would you do that? Good question. Oh, this is why you would do that. In this situation, you've got a pretty funky shape. And all they've done is they've given you an area, a coloured in area, and a height. So how is that important to me? Well, ladies and gentlemen, they're trying to ask you to use the volume in a different way. So we have volume is area of cross-section times by height. Do I know the area of cross-section? Let me think. Yes, because they've got a flipping big thing there that says area and an arrow to it, and they've even coloured it in for you. So they've given you the area of cross-section, which is actually in this situation 10, multiplied by the height, which is 5, which gives me 50 centimeters and cubed. Oh my God, this stuff is so easy, but they're going to try and trick you. Sometimes they don't give you the area of cross-section. Well, it doesn't look like they have, but in fact they have. Imagine I put a cuboid that's rectangular through a bread slicing machine. Now this area here, believe it or not, is going to be exactly the same as the area at the back. That sort of makes sense, doesn't it? Yeah? But it's also the same as if I was to cut out an area in the center. So maths is nothing more than a big fat trick. And so in this situation here, they're basically turning around and saying, well, the area of cross-section is that colored in section. But they haven't given it to you. You've got to work it out. Because if we look at the front of that shape, what is it? It's a triangle. And how do we find the area of a triangle? Base times height and halve it. So we know the base is 4. We know the height, it says, is 3. So therefore, the area of cross-section is a half base times height. Well, I'm going to do 4 times 3, which is 12, and a half of 12, which gives me 6. And so I have 6 centimeters squared. Remember, centimeters squared because it is an area. And now we know the volume is going to be given by the area of cross-section times by the height. Now again, in this situation, it's not height, it's probably length back. Doesn't matter. Who cares what we call it as long as you get the calculation the right way around. Area of cross-section was 6. How far back is it going? 6, which gives me 36 centimeters. And in this situation, don't forget the floaty 3 because it is volume. Volume, yes? There are gotchas, ladies and gentlemen, yes? And it's just because they give you diagrams here that are there, they are there to try and trick you. But the point of it is, in this situation here, find the area of this front section here and multiply it by how far it goes back, yes? Is that an obvious shape? Not necessarily, but do we have the formula somewhere else? Of course we do, yes. So don't stuff it up. Just make sure you don't get tricked by the gotchas. Here's another one. Looks difficult, doesn't it? Yes, they're rambling on about a swimming pool. Yes, I don't care about the swimming pool. The area of that shape, the volume of that shape is going to be the area of the cross-section, yes, times by how far back it goes. So in that situation, you would be looking at finding the area of the shaded section as well. Now, it's a composite shape. What you'll notice is you've got this shape here, which is a rectangle of 10 by 2.5, and you've got this shape here, which is a trapezium. Yep, so you've got your trapezium because that's 1.5, and you can find this distance here, and you know this distance here. And so as far as I'm concerned, you have everything you need to do to find the two areas. So you'd find that area, call it area 1. You'd find that area, call it area 2, and you would know that your area of cross-section is area 1 plus area 2, and then your volume would be area of cross-section times how far back it goes, which in that situation is 15 meters. Last gotcha, all right? And again, maths isn't just about getting you to do simple questions. We're going to start linking it together for you. So now we're going to throw in algebra again. And we can use algebra for our answers as well. So for example, what would be the volume of a cube with side length x? Now we've got a cube. We know what a cube means. It means that all the sides are the same length. So that's x, and that's x. Now again, with a cube or a cuboid or something along those lines, we only need 3 side lengths, because once we found the area of the cross section, we can multiply it by how far it goes back. So here is my cross section. My area of cross section is equal to, well, x times x, which again, your algebra shows that we can write that as x with a floaty 2. I don't know what my units are. I could probably put units squared to show that it's an area. And so what's my volume? It's area of cross-section times by height. All right, in this situation, that's my height, more a length. And so I'm going to do x squared times x, which again comes down. Now, funnily enough, this is where your volume finishes. Your volume is done now. Now you're going back to algebra. So in this situation, that becomes x cubed, and you would write the units with a floaty 3, and that is it. Job done. That's all they want from you, yes? So the basics of this type of work is, can you understand how to find the volume using the area of cross-section and some sort of length or height, and can use algebra as well? Well, there we go. Another lesson done. Tick. Thank you very much for watching. I'm Darren, otherwise known as MaffsGuru. Subscribe if you can to my YouTube channel. Head over to MaffsGuru.com and there's videos on there for you. Otherwise, I'm going to call it a day. Thank you so much for watching. Spread the word. Tell your mates. But I'm calling it a day. Speak soon. Take care. Bye-bye.